Good morning. We are going to begin here with our Math Live lesson on prime factorization, which is lesson 9.2 in our book. We are also going to be working through lesson 9.3, which is order of operations. So we'll have both of those going. Let me just kind of get things set up here. Feel free to jump in and join us at any time. And let me make sure that you guys can see. Okay, good. Might be a little choppy, but we've got this going now. And let me see if I can maybe make it a little less choppy, optimize for less viewer buffering, interaction. All right, I think we're gonna be good. We're gonna just go with this. If you join us, if you're joining us live, again, feel free to go to the YouTube actual link. That way you can chat with us. If you're watching this after it's been recorded, thank you for joining us in that way. And I hope that you'll get something out of this. So, and if you are joining me in chat, would you let me know that everything's working? I know it's terrible. I should be professional at this, but I am not. So you can let me know, hey, Mr. Weichert, we can see your screen or we can't. I can hear you or you can't hear me or anything like that. All right. Well, let's get started. Prime factorization. Let's start with this problem. Anna wants to build a rectangular garden with an area of 24 square feet. So without really going further, knowing what exactly we're going to be asked, I can at least draw a rectangular garden, right? Which would just be a rectangle shape. And we do know that it has an area of 24 square feet. An area is, of course, the inside. If we split this garden into squares, and this is not going to be to scale, but I just want to make a point that if these were square feet, 1 foot by 1 foot squares, this is telling us that there would be 24 of them inside. 1, 2, 3 by 7, so this would be 21. Oh, it was close. We could add 3 more and it can actually have the 24 square feet. But let me take those lines out because it doesn't really matter. We just need to know that, yes, the inside of this is 24 square feet, which is feet squared, like that. The question is, let's see, what are the possible whole number lengths and widths of the garden? So we're trying to find the lengths and widths. What is a possible length? What's a possible width that could go here in order to have these 24 square feet in the inside? Well, all we need to do is think about, because if area is length times width, then this 24 square feet has got to be something times something. So we're looking for all of the factors, right? Those numbers that when you multiply them together will get you 24, all the factors of 24. So, hello, I see someone is here. Hello. Can you hear me? I'm going to ask if this person can hear me. Okay, so we are looking for all the factors of 24, going back to this. So we can just start listing factors of 24, right? 24 is going to be equal to 1 times 24, right? I guess I can start working kind of like this. 1 and 24, 2 and what? 12. 12 will be the next one. What else? 3 and something. 3 and 7 would be 21. 3 and 8 would be 24. Am I going to have enough space here? Maybe, maybe not. 4 and something? Yeah, actually, I'm not. I'm going to run out of space. 4 and 6. And because 5, which is in between 4 and 6, you can't multiply it times something to get 24. We know we're done. So these are all the factors of 24. So we can now say that, well, we could have a length of 1 and a width of 24, right? So that's one possibility. We could also have, actually, I guess I can leave all these possibilities up here. We could have 2 as the length, and then what would be our width? It would be 12. We could have 3, and what did we say? 3 and, oh, whoops, not 12. That was the other one. 3 and 8. And we could have 4 and 6, right? 4 and 6. And that's it. So we have 4 combinations, it looks like. It was 2 and 12, 4 and 6, 24 and 1, and 3 and 8. What are the possible whole number lengths and widths of the garden? Those are all the possible lengths and widths of the garden. Also, I mean, you notice that we could flip this around. These could be lengths and these could be widths. And there could be any number of combination, but we know that it's always going to be these pairs. Whether this is length or width and this is length or width, that pair will always be together. Same with this and these guys. So, all right. Oh, someone who's just joining us in chat is just asking, what are we learning about? We're working on prime factorization, which is finding all of the prime factors of a number, which we'll talk about in a second. On this previous problem, we were finding all of the factors of a certain number. These aren't necessarily prime, but these are all factors of 24, right? 24 was our area, and we tried to find all the factors of them. So just to remind you, factors are any numbers that can multiply with other numbers to get a sum. In this case, right, this is a factor of 24 because 6 times 4. So this is another factor, give 24. 24 and 1 are also factors of 24 because you can multiply them together. Prime numbers are any numbers that have no factors apart from 1 and themselves, okay? And actually, a prime factor only has 2 factors. 1 is not a prime number because it has it only has itself. It doesn't have to. Anyway, I'm kind of getting into things a little further than I need to. But let's take a look at this next problem, though. Okay, Ray Sean is designing a mural. The mural must have an area of 42 square yards. What's the possible whole number lengths and widths of this mural? So, similar type of problem. We have some shape. We just had, it's just a mural, so we don't really know what the shape is, and that's okay. We do know that it has 42 square yards, so I can put 42 square yards squared like that, and that would be 42 squares inside of here made up by 1 yards. Remember that? Okay. Now we're looking for possible whole number lengths and widths. So the same type of thing. We're just looking for all of the factors of 42, in which, if we think about this, could be 1, could be on this side, and 42 on this side. I mean, that'd be a really skinny and long mural, or vice versa. But it still could work. Those are factors. We could have 2 times what? 2 and 21. Is 3 a factor of 42? No. Is 4 a factor of 42? No. 5? No. 6? 6? I'll come back to that one. 7? We know 7 is, right? 7 times, wait, there we go. 7 times 6, right? Sorry. So 6 is a factor of 42. We also have 8, no, 9, no, 10, 11, no, 12. And actually, if I would have written them out like this, we could have said 1 and 42, 2 and 21. And because there was no other number up till 6 and 7, I think that we have them all. Here is a quick way to see if we have them all. We can use a ladder method where we just start taking numbers out. I'm going to take a 2 out, and that's going to leave me with 21. And then I could take a 3 out from 21. That'll leave me with 7, and that's it, right? So I have, notice, by the way, these are prime numbers. So the prime factorization of 42 would be 2 times 3 times 7. So we know that we can multiply 2 times something, 3 times something, and 7 times something, and that's what we've done. So possible combinations could be 1 and 42, 2 and 21, and 7 and 6. All right. Possible whole number lengths and widths. We figured that out. Excellent. Okay, here's what we're going to do now. Now we're going to look solely for the prime factorization. Okay, and we're not just going to list out all of the factors of 21. Instead, what we're going to do is we're going to find only the numbers that are factors of 21 that are prime. And in this case, it's going to be fairly easy, and we could just list them. But I want to show you some different methods of doing this. So let's start with something called a factor tree, prime factorization tree, factor tree. And it's going to start by having that product, right, our whole number at the top. And then we're going to branch out. And each time we branch out, we're going to come up with a prime number that we can take out. So what are two factors of 21? One of them being a prime number. Well, 2 is a prime number, but 2 is not a factor of 21, so that doesn't work. 3 is the next largest prime number, and 3 does work, so we could say 3 times 7. I'm going to circle every time I get a prime number. So 3 times 7, and so now I could branch off 7 if I can. Is there any factors other than 1 in itself of 7? No. So we're stuck with 7, and actually 7 is a prime number if you recognize that right off. So as far as prime numbers go for 21, we have 3 and 7. If we wanted all the factors of 21, it turns out that it would just be these 4, right? Because you have these 2 that multiply together and these 2 that multiply together. But if we're talking about prime numbers, we're only going to have 7 and 3. And how you would write this as in prime factorization, you could just say 3 times 7. That would be kind of a prime factorization of 21. Okay, 37. We could list all the factors of 37. We could say 1 and 37. And then, gosh, is there any other factors of 37 besides 1 in itself? 2 times something? No, because it's not even, so 2 is not. 3 times something? No, because I know that if this was 33, that would be 11, and 36 would be 3 times 12, and then 39, and 37 doesn't fit in there, so 3 is not. 4, I think that you can realize right quick that we're done. These are going to be the only factors of 37, and that's it. So, oh, by the way, because those are the only factors of 37, that makes 37 a prime number because it has only 2 factors, 1 and itself. 42. You know what? We're going to skip this one, and we're going to skip this one. Okay, let's move to this. 240. So we're going to use the factor tree here, prime factorization, and we're going to list out any prime factors we can think of. We can start with the most simple one, and that would be 2. In fact, let's do that. And I know 2 is prime, so I'm going to circle it. And then if we take 2 out of this, what are we left with? That would be 120. And 120 is surely not prime. I can take out another 2. And that will leave me with, what would this be? So divide 100 in half would be 50, and plus half of 20 would be 10, so that's 60. Okay, 60 is not prime because I know I can take factors out. I can take another 2, and that's going to leave us with 30. And it could do that. Uh-oh, am I going to run out of space? Yeah, I think I will. Should have wrote smaller. That's going to be 2 and 15. 15, I'm just going to go this way, and it's going to look terrible, but it's okay. 15 is going to be 3 and 5. And 3 and 5 are prime numbers. So now I'm done. When I have only prime numbers left, then my prime factorization is finished. And I'm going to take all those prime numbers, I'm going to count them up like this. In fact, let's start with, we'll start with the smallest one. So let's start with 2. Do we have more than 1, 2 of prime numbers? Yeah, we have 1 here, 1, and 1. So 1, 2, 3, 4 2s. Now, because of our last lesson of exponents, we know that we can write that instead of saying 2 times 2 times 2 times 2, 4 times, we can say 2 to the 2 to the power of 4, 2 to the fourth, 2 as the base, 4 as the exponent, and that is symbolizing all of these 2's right here, just in a shorthand way. And then we have these two guys left, and since there's only 1, 3, and 1, 5, we're just going to write them that way. Say multiplied by 3 and multiplied by 5. And so we have done a prime factorization of 240, and this is saying all of the prime factors of 240 are right here. There are 4 2's, 1, 3, and 1, 5. And when you multiply these things together, if we were to multiply this out, that would be 2 times 2, which is 4, times 2 times 8, times 2 is 16, times 3 times 5, you'll find that we have this 240. Prime factorization. Now, before we move on from here, let me show you another way that you could do this. In fact, we did it just a minute ago, similarly, and we can call this the ladder method, and that is where we write the number that we want to do a prime factorization of here, and I can take out, again, it's going to be the same kind of process, right? We could take out the, if we start with the biggest prime that we can think of to take out, that's helpful too. And I know just looking at this number, because it ends with a 0, we can take out a 5, and that's a prime number. So I'm going to take out, remember, only taking out primes. So we'll take out a 5, and that'll leave us with, what will that leave us with? We take out a 5, 16 times 3. Sorry, let me do my math real quick. Maybe you guys could help me out here. 1848. 48 times 5. Let's see. I think it is 24. Yep, that's right. Okay. 48 is the number we're looking for. All right. So we're left with 48 is what we just found. Okay, when we take out that 5. Can we take out any prime numbers from 48 apart from 1? Yeah, we can. We can take out at least a 2. When we take out a 2, we'll be left with 24. And take out another 2 from there, and I'm left with 12. Take out another 2, and I'm left with 6. Take out another 2, and I'm left with 3. And we're left with only prime numbers, 5, 2, and 3. And what do you know? Look at this. There's our 4 2's, 2 to the 4th power, 2 times 2 times 2 times 2, 2 times itself 4 times 3, times 5. So we can use a factor tree, prime factorization kind of tree. We can use this ladder method. We could have also, if we wanted to, listed out all of the factors of 240 and then circled the ones that are prime. But that would have taken a while, okay? And I don't recommend doing that, because you really wouldn't have saw how many 2's that you need, right? It wouldn't have shown you 2 times something and then 2 times something else. It wouldn't have worked that way. So let's not use this one when we're trying to find prime factorization. Let's use the tree or the ladder, and let's try another problem. So we have 132. I'm going to use the ladder method just because I like it, but you're free to use any strategy you want. 132, I'm going to take out, I guess I'll just start with 2. And if I take out a 2 from there, I'll be left with 66. And I know I can take out 2 from here, and that'll leave me with 33. Any prime numbers I can take out, prime factors, I can take out a 3, and that'll leave me with 11. And can I take out any prime factors from 11? Well, actually, 11 is a prime number, so we're going to leave it like that. And we can't take out any more factors, so we only have prime numbers. And so now, to write this in shorthand, hey, we're getting more people joining us. Nice, excellent. Can you guys tell me, based on what well, actually, if you're just joining us, I guess I'll answer this for us. What we just did is we found all of the prime factors of 132 by using a ladder method, meaning we took out prime numbers of factors. So I took out a 2, left us with 66. Any prime numbers I could take from here? Yes, 2 leaves us with 33. Take out another prime factor, and we're left with a prime number. There's nothing else we can take out. So these are our prime numbers. We can write this in shorthand now from what we learned about exponents. And that is, these two are the same, and there are two of them. So we'll say that's 2 to the second power times 3 times 11. And this is a prime factorization of 132. Let's try another. Okay, this is another problem just like the first ones we did where we're trying to find the area. No, not find the area. We have the area. This one looks like it's square feet. And we need to find out what it would be the length and the widths that we could use for this. And again, we could use the ladder method. Whoops, excuse me. Could do something like this. It looks like I could take out a 2. Let's see, that'd be 36. Take out another 2. That would be 15 plus 3 would be 18. Another 2 would be 9, a 3, and a 3. So one way we could actually say this, instead of, I mean, we're not answering what are all the possible whole numbers in this sense, but if we wanted to write this, we could say, hey, there are 1, 2, 3 2s, so 2 to the third power feet. And look at that, 2 3s, so it's 3 times 3, so 3 squared feet. And so this is actual possible combination for length and width in order to get this, right? 2 times itself, 2 times would be 2 times 2 times 2, which is 8. And this is 9, so 8 times 9, which would be 72. Anyways, I didn't answer this question correctly. You could do this from based off of the first problems we did. If you need help with that, you can go back to those first problems. I just wanted to look at the prime factorization of that. Yeah, but we're going to do, I mean, basically the rest of lesson 9.2 is the same thing. In fact, we're just finding the prime factorization, and I'm going to use the factor tree on this one. Again, prime factorization. Hopefully I won't run out of space. Let's see if I do it smaller. Okay, I'm going to take out a prime number from 36, and I know I could take out a 3. I know that's prime, so I'm going to circle it. And let me make sure I'm getting everybody. I'm not getting, let me see. Okay, there's your comments. Nice. Okay. If I take out a 3 from this, I'm going to be left with 12, right? And 12 is not prime, so I won't circle that. In fact, I'll break it down even further. I could take out a 3, and that leaves me with a 4. I know that's prime. 4 is not prime because I can break it down further to 2 and 2, and 2 is prime. So 36 broken down is going to be 2 3s and 2 2s, and so we can write it like this: 2 3s and 2 2s, and 3 times itself 2 times, and 3 times 3 times 3 and 2 times 2. There we go. And that would be the prime factorization of 36. Hey, yes, we have more people joining us. This is excellent. Any questions you guys have there in live math land? If you're not watching this already recorded, please shoot me any questions if I'm moving too fast, or if you're just jumping in and you're kind of questioning what we're doing, let me know, because I'm just kind of flying through this. So I just used a strategy right here that we call factor tree or prime factorization using a factor tree. And we are breaking down each number into factors, whereas one of them's prime. And so when we get to a prime number, we circle it and we stop on that branch. And the other branch, we keep dividing until we get another prime and divide until we end up with prime numbers. When we have all of our prime factors, we then group them together. So 3 and 3, so that's 3 times 3, and 2 and a 2, so that's 2 times 2. And we write it with exponents, okay? So that's a prime factorization of 36 is 3 squared times 2 squared. But we have another method that I showed earlier, and that is a ladder method. And so we'll use that for 32. And you just write your first whole number there, and you start taking out prime numbers again. So it's very similar to this. It just looks a little different. And so a prime number we can take out from 32 would be, we could say 2. And 2 times what? 2 times 16. And 16 is not prime, so I'm going to put it in a next step. And I could take out another 2, and that's prime. That's going to leave us with 8. And we can take out another prime number for sure, 2, and that's going to leave us with 4. And we could take out another 2, which is prime, and we're left with 2, and that's also prime. So I wouldn't box it in because there's nowhere else to go with 2. It's prime. So we're done. So the question is, what is the prime factorization then of 32? Well, it would be 2 to what power? You tell me. 2 to what power is the prime factorization of 32? Given those people that are live online an opportunity to comment. All right, I got a comment. Yeah. Okay. 2 to the 5th power. Sweet. And how did you get that? You got that because you counted these guys, right? So we have 1, 2, 3, 4, 5. And so 2 times itself 5 times is 2 to the 5th power. Good. So 32. Good. So that was it for lesson 9.2. A super easy, quick lesson. I want you later, okay, because I'm going to actually right now move into lesson 9.3, and you're fine to step in and step out of this recording whenever you want to. But for lesson 9.2, I'm asking that you choose any 10 problems to solve in the independent practice on page 249 through to 250. Okay, any 10 problems. So that's your homework for lesson 9.2. But I'm going to move on here, and I'm going to go back to the gallery, step out of this for a second, step into this. Aha, there we go. Okay, order of operations. This more than likely is going to be a review also, as much as the other one was, I hope, because order of operations is something, at least in class, that we've talked about. Let's take a look at this problem. Amy and 3 friends launch a new website. Okay, you know what? I'm going to start by just doing Amy and 3 friends. Okay. I don't know what I'm going to use these for, but I just have Amy and 3 friends. Okay. They launch a new website. So this is the website launching team. Each of the 4 friends, okay, 1, 2, 3, 4. These are all friends, 4 of them. Each of them emails the web address of their new website to 3 new friends. Okay. Each of the friends email their new website to 3 new friends. So that means Amy, she's going to email to 3 people. And this person is going to email to 3 people. And this person is going to email out to 3 people. And this person is going to email out to 3 people. Something like that, right? That was a really bad one. Okay. So they're emailing out. Okay. What else? These new friends. Oh, bother. I need to draw them. So here are the new people that get the websites. So these new friends forward the web address to 3 more friends. Oh, goodness. Okay. So these 3 new friends, 1, 2, 3, 1, 2, 3, 1, 2, 3, 1, 2, 3, is going to look, whoa, I'm going to run out of space. 1, 2, 3, 1, 2, 3, 1, 2, 3. Whew. Something like this, okay? New friends, these were the new friends. They forwarded out to 3 more friends. If no one receives the email more than once, how many people will receive the web address in the second wave of emails? The second wave. Okay, so where is the first wave? Well, we have Amy and her friends, right? And the first wave of emails would be these pink, right? Going, the emails going out. So here's the first wave. Here's the recipients of the first wave. Am I right? Let's see. How many people receive the website in the second wave of emails? The first wave is sent out, and this is the recipients. And the second wave is here. Yeah, this is the second wave, okay? So, I mean, because we drew this out, we could just say, we can count, right? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, 21, 22, 23, 24, 25, 26, 27, 28, 29, 30, 31, 32, 33, 34, 35, 36. 36. Now, that's great. I love the power of drawing and being able to visualize things, but if this was any larger, it may not be worth it, and it may not have been even worth it for us to draw this much because it took a lot of time to draw this. Instead, what we could have done is recognize that in the first wave, we have something that we could say, we could call it, let's see, there were 3, right? I'm looking at how many they sent, right? 3, first to the power of, what could we say? 3 to the power of, and let's just look at Amy, actually. Let's just focus on Amy, okay? Let me get another color. By the way, here's Amy, okay? Here was Amy. Let's do whatever Amy is, and then if we can figure out what hers might be, then we know we only need to have that same thing multiplied 1, 2, 3, 4 times, right? There's 4 of these. 1, 2, 3, 4. So let's figure out Amy, and then let's find it 4 times. Wait, 4 times. Yeah. Okay, so there we go. Let's figure this out. So I have 3 here because Amy, in that first wave, mailed out 3. Okay, that's like 3 to the first power, right? It's just 3. But then those 3 emailed out again, 1, 2, 3, 1, 2, 3. And so now we have 3 to not just a first wave, but a second wave, 3 groups of 3. 3 times 3. 3 times 3 is an exponent's 3 squared, okay? What I hope that you realize is we didn't just say 3 times itself 3 times, because that's not what's happening. We have 3 times 3 groups of 3, right? 1 group, 2 group, 3 groups of 3. So this is 3 groups of 3. 3 groups of 3 is 3 times 3, which means we have 3 squared. Woo, kind of confusing. But let's see if we get the same amount. Remember we got 36 when we counted? Well, what is 3 times 3? Okay, that's 9. And we have that times 4, right? Bring that down. What's 9 times 4 equal? 36. Woo! Yeah, so the confusing things that could happen here is not recognizing that we're doing one thing 4 times, right? Whatever this is, we were doing it 4 times. 1, 2, 3, 4. In fact, if I just made these all different colors, we could see them a lot better. Like that, right? These are equal. Whatever's inside of these there's 4 of them. So we have 4 of whatever Amy is. So I decided to do Amy. I looked at Amy and I said, okay, there's one wave of 3, and then there's another wave of 3. So that's 3 groups of 3, or 3 squared. And we found 36. Woo! Okay, now, when we're working with order of operations, it's important that we know, what we're supposed to do first. Otherwise, we'll get completely different. We can get different values and different answers. I know that most of you already know that the order of operations is, some of you guys call it PEMDAS. Some of you call it please excuse my dear Aunt Sally. And what do these letters represent? Well, we have P as always doing whatever's in the parentheses first, performing operations in the parentheses. Then you're always going to do you're going to find the value of anything with an exponent. That's what the E is for exponents. Then, like we talked about in class the other day, the next step is multiply or divide, whichever comes first, moving left from right. And lastly, add and subtract, whichever comes first, going left to right. And we'll do examples so that you guys can see these things. But just to point out, there are really only 4 steps in the order of operations. Parentheses, exponents, multiply, divide, add, subtract. 1, 2, 3, 4. And let's try this over here with this expression. So we have an addition operation, we have a division operation, and an exponent operation. And it's just helpful for us just to start over here and ask ourselves, are there any parentheses? And no, there aren't. So let's move to exponents. Are there any exponents? Yeah, I don't know if this is hard to tell. I tried to make one, but this is an exponent, 3 to the 2nd power, 3 squared. So let's solve that first. And we know 3 squared is 3 times 3, which is 9. And then we have all the rest the same. Okay, so we've now done the exponents. We've now moved to multiply or divide, moving left to right. So left to right in multiply or divide, no. Multiply or divide, yes. So it looks like we're going to do this first. So 18 divided by 9 is 2. And we have whatever is left over, and we still have that plus 5. Okay, yeah, 5 plus. And we look down, add and subtract. There's only one more thing left to do. And so now we know that we'll do that, and we'll get 7. Okay. And again, if we would have done this another way, where we would have added these first and then tried to divide by that, it would not come to the same. We would not have had the same solution. Because first of all, this is 9. So something divided by 9 equals 7 would have to be 63, correct? And that is not going to equal 63. So yeah, we have to agree on a set of rules of how this will work, and someone's come up with those set of rules. So let's try this one. Let me put out my parentheses, exponents, multiply, divide, add, subtract. Let's do this again. 21 plus 3 squared divided by 3. Are there any parentheses, Mr. Reichert? No. Are there any exponents? Yes. So we're going to work on that first. So 21 will remain the same. The plus will remain the same. This will not. That will now be 9 because 3 squared is 9. But we still have that divided by 3 sign at the end. Okay. So this, no more exponents, multiply or divide, plus and divide. So here's a division problem. So we're going to do that. And that'll equal 9 divided by 3 is 3. And we're left with 21 plus 3. And that's our add or subtract. And plus it's the only thing left to do. And so that'll be 24. You guys have any questions? I know I'm flying through this. I'm hoping this, again, is kind of review. It might be helpful, by the way, to always write down PEMDAS or however you want to remember that off to the side and circle this guy and circle this guy, because remember there, it doesn't mean multiplication comes first. It just means whichever of these come first, going left to right. So again, parentheses, there are no parentheses. Exponents here, yeah, we have exponent. So I'm going to write 6 times whatever this guy is going to equal. So 2 times 2 times 2. So 2 times 2 is 4 times that last 2 is 8. Okay. Get rid of this. Okay. That equals 8. We still have, whoops, this division and this addition. So exponents, no more exponents. Multiply or divide. Oh, multiply right here. 6 times 8. 6 times 8 is 48. And we have divide by 3 plus 1. And multiply or divide. Yep, there's a division. 48 divided by 3. Whoa. 48 divided by 3. That one I do not know off the top of my head. Does anybody know 48 divided by 3? Let's see. 6, so we could say it goes on at 1 time. 18. Hey, 16? Is that right? 6 and 3 is 18. Hey, 16 times 3. I should have known that. That's okay. 16. Good. All right. So we know that this now, I know, Mr. Weichert now knows that that's equal to 16. We have plus 1, and that's our only operation left, so 17. Okay, any questions about this? Again, this is another simple lesson. I'd like for you guys to try this one on your own, just so I can make sure that you guys have this down. So you could either do this in your head, or if you have, hopefully you have paper and pencil next to you taking notes. Try this one out. If you're with me on chat, you can put your answer up on there. All right, I have some people responding. Let's see if you got this correct. So parentheses, exponents, multiply, divide, add, subtract. That doesn't look like an S. There we go. No parentheses. Okay. Exponents, yeah. So let's do that first. 9 times 9 is 81. So we have 7 plus 15 times 81. Exponents are done. Multiply or divide, I see a multiplication problem here. So we have 81, whoops, times, let's multiply, times 15. So let me use a different color. 5 times 1 is 5. 5 times 8 is 40. I have 10 times 1, basically, or 1 is 1. It's 10. 10 times 80 is 800. And we have 5 and 12. All right. Now we have 1,215, and we can now replace that right here, plus 7. And so plus 7 will be 1,222. Yeah, Mega HBot. Me and you on the same page. Sweet. And I hope you guys that are watching this pre-recorded got the same solution. I'm going to move on, though. We have some bigger fish to fry. I'm going to skip that one. Okay, now we're going to, again, get into some that are a little bit more difficult. Parentheses. In this case, we do have parentheses, so we need to solve that first. And inside the parentheses, we also need to do this. So luckily, there's only one operation inside the parentheses, and it's division. So we're going to do 9 divided by 3. So I'm going to rewrite this problem 4 times whatever our solution is in our parentheses. What's 9 divided by 3? That's going to be 3. And we still have this squared, so I'm going to bring it down over here. So now we have 4 times 3 squared. And we're done with parentheses. Do we have any exponents? Yes, we do. So we're going to do that. 3 squared is not 6. It's 3 times 3, which is 9. And we have times 4. And we're done with our exponents. Multiply, divide. Yep, that's our only operation left. So that's going to give us 36. And we're done. So this one was only different because we had a parentheses, but you may have more than one operation inside the parentheses, which means you'd have to do this over again inside the parentheses. We have another one like that. So we have a parentheses. I'm not going to write down my PEMDAS because I'm just going to remember now. Parentheses first, parentheses first. Okay, sweet. So this is going to be 10. I can rewrite the rest of the equation around it because nothing else changes. Now exponents, P, right? Parentheses exponents. So this is going to equal 10 times 10. It's 100. And we only have one operation left, and that's to add. And 100 plus 53 is 153. Sorry to fly through these, but I mean, I'm hoping that you just are getting this repetition and you're seeing how this is done, and you're just remembering that PEMDAS, parentheses, exponents, multiply, add, subtract. All right, you guys, are you here? I just lost my connection. All basically. Can you guys hear me? Is everything okay? Is it back up? I was new. The internet just told me that it dropped my call. Are you guys okay? Good. It sounds like it's working back. Okay, good. Sorry about that. So back to the problem. John wants to evaluate this expression. As a first step, he writes 5 squared plus 3 squared. Will he get the correct value for this expression? If not, what should he do to evaluate? So here's what John did. Let's write it out. He has original expression of 5 plus 3 squared, and he is saying that this is equal to 5 squared plus 3 squared. And let's solve the rest of this for John. Let's see what he gets, and then let's go back and do order of operations ourselves and see if we get the same answer. So 5 squared is 25, right? 5 times 5. 3 squared is 9. And so ultimately we have 25 plus 9, which will be 1 less than 35, because this is 1 less than 10. If this was 10, then that would make this 35, but it's not, it's 1 less. So this is going to be 34. Not right now, thank you. Yeah. So we get 34, okay? So we know that John, he got 34. Now we're gonna solve this using what we know to be correct. And we're gonna see if we get the same thing. So parentheses first. In this case, parentheses first is doing this. It's not doing the exponents. So 5 plus 8. Actually, I'm sorry, let me just write it out for us. All right, so parentheses first, that would be 8. And so we're left with 8 squared. And whoops, 8 squared is 8 times 8, which is 64. So we got 64. John got 34. We both cannot be correct. So because we can't both be correct, only one of us is correct. Only one of us is correct, and because we used the agreed upon order of operations throughout all mathematics, we are correct, and John is not. So I guess to answer the question then, will he get the correct value? Well, no, because we worked it out. No, he won't. What should he do to evaluate the expression? What did he do wrong is the bigger question, right? Not just, yay, we got it right and you didn't, ha ha ha. But what did he do wrong here? And how could we help him? Excuse me. Notice, are you guys being able to see my screen moving? Okay. I think so. Yeah, it looks like. Notice that he went straight to exponents. He took this exponent and he decided to give it to all of the add-ins inside of the parentheses, right? 5 squared, it's the same. This is the same as 5 squared plus 3 squared. Well, but no, it's not in order of operations. That's not how it's going to work. And so we had to do what was inside the parentheses first. And we got 8. And then we squared 8. Okay. So what did he do wrong? He didn't follow the order of operations, and we did. All right. I'm getting a lot of people saying I'm cutting out. I apologize for that if that's the case. I think we're having a bad connection. When this is recorded, and for those of you who are watching this later, let me know if I'm cutting out or if the video was pretty okay the whole way through. But let me just do one more problem with you guys, and then we'll be done. So we need to have our order of operations. And we're going to start with parentheses. And that's right here. 20 divided by 4 is 5. And so I'm going to write the rest. 5 times 5 and then squared. And now we need to do exponents, which is right here. And that'll equal 25. 5 times 25. Oh, oops. 5 times 25. And we're done. And 5 groups of 25 would be 125. All right, I said I'd only do one more problem. I hope that it's caught on. I hope that you guys have seen enough examples. I want you to do the same thing as what I asked for lesson 9.2, and that is choose any 10 problems from the independent practice, which is found on page 255 and 256. Again, I apologize for that dropout in the middle of the recording, but these were 2 short lessons that I feel like you guys can get easily. And I'm going to call it a day. If you have any questions further than what you guys are talking about in the chat, feel free to let me know in Google Classroom. And I'm going to post up an online quiz for lesson 9.2 later today. And probably tomorrow I'll post up a quiz for lesson 9.3. But that's after you do the independent practice stuff for lesson 9.2 and 9.3. All right, guys, I will talk to you later. See ya.